Hello, I'm Brian Young. Today we're going to go over 26402 healthcare facilities, the NCCER. Let's take a look at 26402. Healthcare facilities, there are different types of healthcare facilities. Inpatient means that you're going to stay overnight. A patient admitted into the hospital for an overnight stay. Outpatient, you're leaving the same day. Patient who receives services at a hospital but is not admitted for an overnight stay. You'll hear another term, ambulatory. It means you can walk. You can get up and walk. So when we're talking about fire alarms and things like that, they usually don't have an actual fire alarm in a hospital because the patients would panic if they are not ambulatory. If they can't get out of bed and all of a sudden there's a fire alarm, they're thinking they're going to burn to death. So instead, they send it down to the nurse's station or to the maintenance department, and they are notified that there is smoke, if not fire, somewhere in the hospital. And they can go to that floor, go to that wing, see if someone is smoking indoors, see if there's an actual trash can fire, or if there's an electrical panel. If they need to evacuate the patients, they can just very calmly go into the rooms and unlock the wheels on their beds, tell them, we're going to go for a little ride, take them over to the elevator, or take them, get them downstairs, get them to where they can be evacuated from the building in case the fire gets out of control. But ambulatory means you can walk. On the right-hand column of page 1, it says, in addition to the National Fire Protection Association 70, that's the National Electrical Code, and NFPA 99, the Joint Commission, it was formerly known as the Joint Commission on Accreditation of Healthcare Organizations, JCAHO. Now they just call it the Joint Commission, period. Addresses emergency electrical power systems and their standards, EC 7.20 and EC 7.40. So the Joint Commission. Down a little ways, next indented paragraph on the right-hand side of page 1 says the installation of electrical systems in healthcare facilities is governed by NEC Article 517 and NFPA 99. We've told you before that NFPA 70 is the code book, National Electrical Code. National Fire Protection Association has written an encyclopedic volume of books. There's over 200 books in the NFPA collection. If it burns, they've written a book about it. So electrical is just one of those books, NFPA 70. NFPA 99 is for healthcare facilities, electrical powered healthcare facilities. Over on the left-hand column of page 2, here on the left-hand side of page 2, hospital is a building or portion thereof on a 24-hour basis for the medical, psychiatric, obstetrical, or surgical care of 4 or more patients. So it's on a 24-hour basis. Limited care facilities are buildings or portion thereof on a 24-hour basis for the housing of 4 or more persons who are incapable of self-preservation because of age, physical limitation due to accident or illness, or limitations such as mental retardation, developmental disabilities, mental illness, or chemical dependency. So this is a limited care facility. Nursing homes are buildings or portion thereof that are used on a 24-hour basis for the housing and nursing care of 4 or more persons. You notice how it's always 4 or more persons who, because of mental or physical incapacity, might be unable to provide for their own needs and safety without the assistance of another person. So these are different types of healthcare facilities. Essential electrical system. These are the electrical systems that you need to have in place for these healthcare facilities. An EES 1, an Essential Electrical System 1. Non-essential loads are those that are not necessary for the safety of building occupants or for safe and effective patient care. Examples of non-essential loads include televisions. Televisions are non-essential. Those are non-essential loads. Down a little further on the right-hand column of page 2 tells us the equipment branch. That's your clue right there. It's equipment. Consists of those items that are needed to operate the facility but are not directly related to patient care. So facilities telephone system. The life safety branch and the critical branch consist of those items that are essential to patient care. The life safety branch supplies power to those items needed to ensure safety of building occupants as well as patients. So life safety isn't just patients. Life safety are nurses, doctors, custodial workers, anyone in that hospital. The life safety branch supplies power to those items needed to ensure the safety of building occupants as well as patients. These include exit signs, stairway lighting, alarm systems, communication systems. The critical branch supplies power to areas that are directly related to patient care. These include pharmacies, emergency rooms, intensive care units, and so on. So life safety is everyone. Critical branch is for patient care. Over on page 4 on the left-hand column, a type 1 essential electrical system. Type 1 EES is required in any facility with a critical care unit or that admits patients requiring electrical life support equipment. So if there's a piece of equipment that's keeping you alive, you have to go to a facility that has a type 1 essential electrical system. Okay. Down at the bottom of page 4 on the right-hand side, it says type 2 essential electrical systems. These are not as stringent. I wanted to highlight that just because it's over on page 6, but they're talking about a type 2 EES, and I even wrote type 2 here on page 6, left-hand column. It says the following equipment may be connected to the equipment branch and arrange for delayed automatic connection to the alternate power source. So this equipment is not specifically for preservation of life. So there can be a delay in the switching over to emergency power. Patient care spaces, task illumination, and selected receptacles in medication preparation areas. So those types of loads, there could be a 30-second delay in switching over to emergency power, and no one would come to any harm. On the right-hand column of page 6, other healthcare facilities. In facilities that do not require a type 1 or type 2 EES. What would that be? Well, if you're going to go to an orthodontist and he's going to surgically remove a tooth, he's going to do a root canal, you will be under some form of Novocaine or anesthetic, but you're an outpatient. In a couple of hours, the anesthesia will wear off and you will leave. You probably won't drive yourself home. Someone will drive you, but you're going to be on an outpatient basis. So it doesn't require a type 1 or a type 2 essential electrical supply or system for an orthodontist. Batteries are required to maintain emergency load for up to an hour and a half without the voltage falling below 87.5% of normal. Okay? So batteries are required to maintain the emergency load for an hour and a half without the voltage falling below 87.5% of normal. And that's again in a facility that does not require either a type 1 essential electrical system or a type 2 essential electrical system. Electrical distribution systems on page 6, right-hand column, very bottom of the page, to ensure continuous electrical service from the utility provider. Hospitals and certain other healthcare facilities are placed on a spot network. We used to call this a redundant network. Now they call it a spot network. We'll see why it was called redundant, and we'll see that it's called spot now. These feeders are installed in parallel so that a fault in one feeder will not affect or produce faults in the other. So over on page 7, there's a drawing here. Figure 3 shows us a spot network. Well, ground fault protection, it says downstream and upstream devices. However, phase of overcurrent devices cannot distinguish between normal overcurrents and ground faults. But now let's take a look at this spot network. You have a substation from the utility in a neighborhood, and it's coming into the hospital on one service. There's a whole other substation in a different neighborhood, a different city block, that comes to another service disconnect in that same hospital, and there's a tiebreaker between them. At any time, you can have one main from the utility serving some of the loads, or you can have the other main from the other substation from the utility serving those same loads or different loads. If you close the tiebreaker, if something happened here at this substation, a bus went off the road and crashed into the substation and took it out, they could open this normally closed circuit breaker and they could close the tiebreaker, and this second utility is large enough to carry the entire load of the hospital. That's why we used to call them redundant, because they had enough load, enough service on each of these to run the entire facility. So either one of these can be taken out and they can open the circuit breaker from that utility and close the tiebreaker, and now they can feed the entire facility with just the one side. And this is a one-line diagram. This is actually three-phase coming in, three-phase 480 or three-phase 13.8, whatever it is they have coming in. They're identical, and you can lose one side and the other side is sufficient in size to run the entire facility. That's why we used to call it redundant. Now we call it a spot network. Spot network. Over at the top of the left-hand column of page 8. Oh, this is the continuation of that one sentence that said phase overcurrent devices cannot distinguish between normal load current and a low magnitude ground fault short circuit current of the same magnitude. For this reason, ground fault detection is used in addition to the phase overcurrent device provided to provide protection. So they're going to have a ground fault circuit interrupter for low magnitude ground faults. Okay. If you have a 20 amp circuit breaker and you've got 15 amps going to ground, that 20 amp circuit breaker doesn't see that as an overcurrent and will not open. But if you have 15 amps going to ground, that's not a good thing. So we're going to have a ground fault circuit interrupter. This is not highlighted, but it's very interesting. It's a generator, motor generator set. When you have electric power coming from the utility, you have an electric motor that spins this rotor. This rotor is probably 4,000 pounds. Once you get it spinning, inertia will keep it spinning. And it's turning this generator, and the generator is generating power. So the way this works is the diesel generator is turning this rotor. Like I say, it's about 4,000 pounds. Once you get it going, it doesn't want to stop. And it generates power, and then there's no fluctuation. Once this thing is up to speed, it's not going to just stop on a dime. It's going to keep on going. And that way they can have power while they're transitioning from utility to generator or from generator to utility. This gives them a lot better quality of changeover. Over on page 11, here's that word again, equipotential plane. We hear it when we talk about swimming pools. The shell of the swimming pool, the diving board, the ladder, the pump, a spa, if you have a spa, whatever you've got, everything that's tied together, all of the metal has to be bonded together. It's an equal potential plane. Well, this is talking about patient care areas, a mass of conducting materials that, when bonded together, provide a low impedance to current flow over a wide range of frequencies. So everything in your hospital room is tied together. You don't see it, it's in the walls, but they've got a minimum of a number 10 conductor that runs around to all the receptacles. It sticks out for the bed. It sticks out, it ties into the sink. It goes into the emergency panel and the regular power panel so that everything in that room is at the same potential, voltage, potential, equal voltage, equipotential plane. That way that there's a lot reduced possibility of a patient getting tingle voltage, or even worse, when they're in an operating room and they open you up, your resistance falls very, very far. Our skin has high resistance. We're made up of what, 90% water. So once you break that skin, the resistance of our flesh and our blood and our bodily fluids goes way down, and a little bit of voltage can cause death. So here on the right-hand column of page 11, it says all receptacles should be mounted approximately 24 inches above the floor for the convenience of patients and staff. We're not going to put them at 12 inches. Hospital-grade receptacles meet nationally recognized testing laboratory criteria for superior electrical characteristics and mechanical strength. If you ever buy hospital-grade receptacles, you'll see that when you try to plug something in, you have to really put some force behind it to plug it in. That's because they want it to take a lot of force to unplug it as well. The stabs inside the receptacle are very, very strong, very high tensile strength of springs holding them together. So it takes a lot to separate them to get the stabs on the male cord cap to go in. And then once they're in, it's hanging on. You have to really pull on it to get it out. Don't pull the cord, pull the cord cap. You pull the cord, you're likely to pull it right out of the cord cap. But it's superior because they don't want these items that are plugged into hospital-grade receptacles to just fall out. Like if you have a loose receptacle at home, you plug something in and it wiggles loose, or you see it hanging halfway out, that's not going to happen in the hospital. Isolated ground receptacles. The grounding on the receptacles themselves is isolated from the yoke and from the metal box. They're normally used with digital electronic equipment, including computers, cash registers, computer peripherals, and digital processing equipment. You'll want to have what's called a clean ground, not a dirty ground. So we don't tie this ground in with the grounding on the metal box. If somebody plugs in a drill motor and pulls the trigger on that drill motor, they will have feedback distortion on the grounding conductor of that receptacle, and you'll play havoc with computers. Back in the 90s, when computers were becoming very popular, that's the problem that they were having. They found that a dirty ground would crash that computer. They were very, very fragile, very persnickety. And a worker could walk into a bank, plug into a receptacle, and pull the trigger on the drill motor to drill a hole in something and crash the cashier's register. So they came out with this idea of a clean ground, where you have a ground that goes from that receptacle all the way back to the panel, through the panel to the meter and out to the ground rod. They would not tie it to the grounding system of the electrical bond for the metal parts. They'd take it out to the ground rod, and that way you had a clean ground and no interference would be felt on that receptacle from other receptacles. So that's what they mean by an isolated grounding receptacle. Tamper-resistant receptacles. These receptacles must be used throughout psychiatric and designated general care pediatric, that's children, locations. So pediatric and psychiatric, people will stick things in those receptacles, so you have to have tamper-resistant. You have to put a blade in both sides, hot and neutral, at the same time in order to get them to plug in. You can't take a paper clip or a screwdriver or something and just push in on it. It's got a plastic window that keeps that blade from going in. When you push both of them, the window will move out of the way, and then you can plug into that tamper-resistant receptacle. At the top left-hand side of page 12 says, this hazard worsens as more equipment is used near a patient, such as in surgical suites and intensive care units. Well, let's go back and read a little bit because we want to know what it is that they're talking about. Over here on page 11 on the bottom, says general care spaces. It's difficult to prevent a conductive path from a grounded object to a patient's body in a healthcare facility. The patient may be, the path may be created accidentally or through instruments directly connected to the patient that are a source of electrical equipment or current. This hazard worsens as more equipment is used near a patient, such as in surgical suites and intensive care units. Methods of reducing the likelihood of electric shock to a patient include the following, and then they give us some bulleted points. We have to make sure that we have that equipotential plane, everything on the same potential. Over on page 13, left-hand side, it says, in addition to 2 branch circuits, each patient bed location must have a minimum of 8 receptacles. And this isn't critical care, this is just a bedroom. Per NEC section 517.18b, if you're spending the night at the hospital in a patient care area, there has to be a minimum of 8 receptacles in that area, and I believe 4 of them have to be on regular power and 4 of them have to be on emergency power. On the right-hand side of page 13, right-hand column, very bottom of the page, NEC section 517.19b1 requires that each patient bed location in a critical care space, there you go, critical care, be provided with a minimum of 14 receptacles. And it says at least one of which will be connected to the normal system branch circuit or a critical branch circuit supplied by a different transfer switch than the other receptacles in the same location. In an operating room, per NEC section 517.19c, operating rooms shall be provided with 36 receptacles, at least 12 of them connected to normal power, at least 12 of them connected to emergency power, to the normal or critical branch. They must be of single, duplex, or quadruplex types or any combination. But 36 receptacles, 12 and 12, 12 on normal power, 12 on critical power. Grounding receptacles and fixed equipment. This is on page 14 on the right-hand side, very bottom of the page. Type MI, mineral insulated and metal clad, Mineral insulated and metal clad cables must have a healthcare facility rating in order to be used in a healthcare facility and be clearly marked as such and terminated using listed fittings. And here's a good picture, even though it's not highlighted. Critical care, 36 receptacles. Okay. No, I'm sorry, that's the operating room. This is 12 receptacles, 4, 8, 12, 16. So I've got bed number 1. Here's patient bed location A, patient bed location B. They both have 8 receptacles. Here, 4 of which are going to the emergency panel 1, 4 of which are coming from emergency panel 2, and 8 of them coming from the normal low voltage panel. Low voltage being 12208, high voltage being 277.48. And then over on page 16 on the left-hand side, there's your equipotential grounding plane. An equipotential ground plane is a mass of conducting materials that, when bonded together, provides a low impedance to current flow over a wide range of frequencies. Okay. Let's take a look at page 18. This is wiring in healthcare facilities. On the right-hand column, 1, 2, 3, 4, 5. The 5th bullet down says attachment plugs and receptacles and hazardous locations must be listed for use in Class 1 Group C hazardous locations. Where would that be? Well, anesthetizing rooms. That chemical that they use to anesthetize you is highly flammable. So if you're using anesthesia, you have to have Class 1 Group C hazardous locations on your attachment plugs. so that they're not going to arc or spark and cause an explosion. Okay. On page 20, on the right-hand side, low voltage equipment and instruments. Low voltage does not mean low hazard. Low voltage equipment that's typically in contact with patients or has exposed current carrying elements must be moisture resistant and operate on 10 volts or less. Electrical power to low voltage equipment must be supplied from an individual portable isolation transformer, isolating the primary from the secondary. Over on page 21 on the left-hand column, they're talking about X-ray equipment installations. NEC Article 517 Part 5 covers X-ray equipment. And the top of the right-hand column on page 21 says individual branch circuits are not required for portable, mobile, and transportable medical X-ray equipment requiring a capacity of no more than 60 amps per NEC section 517.71b. Disconnecting means rating of supply conductors. It says for diagnostic equipment, the amperage of supply branch circuit conductors and the current rating of overcurrent protective devices must be no less than 50%. Down a little ways further, it says for diagnostic equipment, the amperage of supply branch circuit conductors at the current rating of overcurrent protective device must not be less than 50% of the momentary rating or 100% of the long-term rating, whichever is greater. So must not be less than 50% of the momentary rating or 100% of the long-term rating on supply conductors. Over on page 23, left-hand column, very first sentence says isolated power systems are used to prevent power interruption. So they're isolated. They might have backup batteries or what have you, and they're going to keep it from being stopped. Here on page 24, on the very bottom of the left-hand column, they're talking about isolated conductors. The first conductor, number one, is orange in color. Instead of brown, orange, yellow, it's orange, brown, yellow. The first conductor is orange. The second conductor is brown, and the third conductor is yellow. Orange, brown, yellow instead of brown, orange, yellow, okay, of the isolated conductors. And then down at the very bottom of the right-hand column on page 24 says monitors must include a a green signal lamp visible to individuals in the anesthetizing area, which remains illuminated when the system is sufficiently isolated. This is anesthetizing equipment and it's isolated from ground, line isolation monitors. You isolate that equipment from ground and there's a green light that's on while it is isolated from ground. If that green light goes out, they have to stop what they're doing and figure out why. They cannot allow it to be grounded in the operating room, because if it's grounded, there could be a spark, and if there's a spark, there could be a boom. So that's it for 26402. This concludes our video lecture. As always, I hope you found this informative. Let me know if you did. If you have any questions, consult your instructor. And as always, work safe, work smart, and wear your PPE. It's there to protect you. You are your greatest advocate for safety on the job site. Don't rely on someone else to keep you safe. All right. Thank you.